for giving me the opportunity to present this collaborative work, as you can see by the number of authors of this paper. And today I will talk about the visual detection of non-natural record in streamflow time series. So data acquisition is the starting point of a learning framework that allow us to make many things. And us as hydrologists, we usually use streamflow measurement to infer the hydrological processes of the catchment. So we use the data for data analysis to understand the catchment functioning. And then we develop some models and use the data to test the model's reaction. And if the models are satisfying, we use them to test some hypotheses, to make prediction or experiments. So we need reliable long-term monitoring of streamflow data to study the water cycle and to have reliable models of the hydrology. But sometimes streamflow measurements may suffer from anomalies due to instrument failures or to interpolation of missing data or due to human influences. So here I presented some examples of actual anomaly that I found in the data sets, such as on the top panel is a linear interpolation for several months. Below you see a drop in the streamflow data that is obviously not natural. You can also have noise, so the cyclical patterns, or some other errors that are punctual. So these anomalies do not reflect natural streamflow dynamics, and we can consider them as disinformative data. And then it is crucial to carefully examine the data before we use it in our study. The problem is that identifying anomalies visually is really time-consuming, and even more using larger data sets. So to our knowledge, no study has focused on the identification of these anomalies in a large data set of streamflow time series. And then question remains on our individual subjectivity for detecting these anomalies in streamflow time series, and also on their extent, so their temporal pattern, and also how they could influence the calculation of hydrological indicator like low flow or high flows. So to answer this question, we made a campaign of visual inspection of streamflow data over a large data set. So we used a streamflow station from more than 600 stations located in France. And the data comes from a French database that's called Hydroportail. And the criteria of the selection of this station was that they were not influenced by anthropogenic activity. The station were also labeled as good quality data by the data providers. And we needed at least 26 years of daily data for catchments larger than 64 square kilometers. And this catchment data set ultimately served as the reference streamflow network for a project called Explore2, which aimed at assessing the impact of climate change on the water resources in France during the 21st century. So to organize the campaign of streamflow inspection, we did online meeting session on Zoom, and this campaign involved the participation of 43 evaluators, mostly from the academic sector. And each evaluator analyzed different number of time series depending on their availability or their preference for specific zones. And the most important thing is that each time series was analyzed by 2 evaluators. So to analyze this data, we provided the evaluator some streamflow time series in HTML format that shows 3 panels. So this is what you see on the left, on the right side of the screen. So the first panel at the top shows the temperature and the fraction of snow at the daily time step. The middle panel shows the precipitation and the discharge time series simulated and observed. So the black one is the observed stream flow. And as the guide, we show also a simulated stream flow in green. And the panel on the bottom is the same, but on log scale. So we can see some problem on the log flow more easily. And also we provided to the evaluator a spreadsheet with one type of station that the person has to analyze, and where the evaluator has to fill the start and end dates of the anomaly and their type as well. And they could comment the anomaly or the overall state of the station. So as I said before, each time series was evaluated by 2 persons. So here on the table, I showed in row the time steps, and in column the 2 evaluators that has reported anomaly. This is just an example. And then we had some question. We asked ourselves how we could combine this feedback. The first option is the union of the anomaly. So if at least one person find an anomaly in the time series, we can consider a time step as an anomaly. So if you see on the dates 2, first evaluator find anomaly A, and second evaluator find nothing, but the union consider that we have an anomaly for this day. The other method for combining the feedback was the intersection. So both evaluators has to identify an anomaly for time step for us to consider that there was an anomaly for that day. So if I take the same example as before, the case 2, if the first evaluator find an anomaly, but the other didn't find anything, we don't consider that there is an anomaly for that day. And by combining the union and intersection anomaly, we can compute the inter-evaluator agreements, so the times of overlapping time step with anomaly between the 2 evaluators. Now let's go to the results. So regarding the subjectivity of the evaluator, here on the figure, I show the time reported as anomaly on the x-axis. And on the y-axis, I show each row is 1 evaluator. And the number on the y-axis is the number of stations that each evaluator analyzed. So we see that the minimum station analyzed by an evaluator was 5, and the maximum is more than 100 time series. So what we see is that the overall median of time reported by the evaluator was 0.7% of the time series. So it's kind of low percentage of anomaly per time series. And the median by evaluator ranged from 0.05 to 3% of time series reported as anomaly. So there is a kind of a high variability, and this could be due to the quality of the time series that we provided to the evaluator, because everyone has different stations to analyze, and these stations are heterogeneous. But this variability could also be related to differences in the level of expectation of the evaluator on the quality of the time series. Now, regarding the agreement between the evaluator, the figure is kind of the same, but the y-axis, the x-axis changed, and it's the inter-evaluator agreement. And now we see that the overall agreement between the evaluator was about 12% of the time reported as anomaly. So it's really, really low. And this shows that identifying some anomaly in the time series is really highly subjective. So it seems that each evaluator has its own intuition of what is the proper time series of stream flow. And this highlights that identification of anomaly is highly challenging, and that we need to find a framework we need to build something to have common practices on how to detect anomalies. And also, since the inter-evaluator agreement was really low, we couldn't use the intersection of anomaly because we wouldn't remove nearly nothing from the time series and no anomaly would be removed. So we choose to remove the union of anomaly from our time series. Now, regarding the temporality of the anomaly and their proportion, here I reported the proportion of time series of anomaly type in percent of total anomaly time. So we see that the most frequent anomaly reported was the linear interpolation for 25% of the anomalies, and the noise as well with 23% of anomalies. Maybe this is due because they are easier to detect or because this anomaly affects longer period of time than the two other. We can also notice that the other type, so when the people couldn't define the type of anomaly, or the disagreement when two evaluators found different type of anomaly are quite high as well. And this suggests that there are some confusion on defining which type of anomaly is in our time series of stream flow. And regarding the seasonal behavior of this anomaly, here I plotted the frequency by month of the different anomalies. And we see that they are more frequent during the summer months, and especially for the linear interpolation and the noise. And this can be related to the low flows that are harder to monitor, or maybe because the stream flow is really low during this period, the human influence is more visible during these months. And the last temporal pattern that we can discuss is the long-term changes in the frequency of the anomaly. And we see that the annual frequency of anomaly decreased from 1976 to 2019, and mostly for linear interpolation and noise as before. And this suggests that there is an overall improvement in the stream flow monitoring since 1975. And the last result is the impact of these anomalies on the stream flow, on the hydrological indicators. So here we computed the change rate of different indicators from low flow to medium flow and high flows. And the change rate is computed as the indicator computed on the initial stream flow time series, and the difference with the same hydrological indicator computed on the stream flow correlated from the anomalies. And we see that the higher change rates are for the low flow indicators, and this is related to the frequency of the anomalies during the summer months. And this could have implication for water managers because they use these indicators as threshold values. However, in contrast, the change rates were really low for the high flow indicators, and this suggests that the wet period were better monitored than the dry period. And as a conclusion, the lessons and perspectives that we learned from this exercise. So for the data providers, overall the data is of good quality and it's improving since 1975, which is a good thing. However, the low water periods can be heavily impacted by anomalies, and here there is room for improvement in the measurement of the low flow. For the data users, So data cleaning is a highly subjective task, and our results suggest that there are some questions on the best practices on how we should clean our data, and even more if we want to make to find some automatic methods to do that for us in a satisfying manner. So yeah, it is really highly subjective, and there are currently no. We need a guideline to how to do it. However, the effect on hydrological indicators was kind of marginal, especially for high flow indicators, and the effect is really visible for low flow indicators. And this is true for our large data sets, because there are still some specific stations where we can see some strong effect of the anomaly on the hydrological indicator. And for the people who are interested in organizing similar campaign of stream flow inspection in the future, we can suggest to keep the number of anomaly types low in order to avoid the confusion between the anomaly, and also to consider to add a confidence index in addition to anomaly types. So maybe we can cover a larger period of anomaly, and the evaluator would report more period where they have some doubts if it's an anomaly or not. And also, we should pay attention to the figure that we provide to the evaluator, because the log scale could magnify the changes in the low flow maybe too much, and maybe this is why we see so many errors or anomaly during the low flow, because the log scale was magnifying some changes that were really low in reality. So that's it for me, and I could answer some questions if we have.
Yeah, first, thank you very much for inviting me and giving me the opportunity to tell you a little bit about the International Soil Moisture Network. So the talk will be a little bit different than the first one, because I'm coming from a data service, and the first part of the talk will be a bit more general on the ISMN, the International Soil Moisture Network, and the second part will then more be about the quality control in our data center and plans that we have. So just a small introduction. I think a lot of you know soil moisture is a very important parameter, because it's partitioned the incoming radiation into sensible and latent heat fluxes, and the precipitation and infiltration and runoff. So it is very important for flood and drought development, and is the basis for our food production. And the ISMN is the largest in situ reference database for soil moisture, and our task is to collect data worldwide from different organizations and networks. We get this data fully free, and this is freely shared by our providers, and we are harmonizing these data sets, and then we provide these data openly accessible to our users via our data portal. We do that to support research in earth science, remote sensing, and water resource management, and especially for satellite-based remote sensing products, and for model validation. So we are a network of networks. That means we are not measuring soil moisture by ourselves. We are completely depending on the voluntary data submission and contributions of our providers. And we are storing not only in situ soil moisture data, of course, we are also storing the metadata for these time series. We are also interested in additional variables depending on the data provider, if this is possible for the data provider to provide these variables, for example, soil temperature, air temperature, precipitation, and so on. And overall, we have about 80 networks in our database. On the right side, you can see the locations of the different networks. Or overall, we have over 3,000 stations with overall more than 11,000 time series, because we measure of course, we get data from different depths. If you look at the data portal, you can also see that most of our measurements are located in the US, but we have also some measurements, let's say in Great Britain, in Europe, and so on. But you can also see that we have a lot of white spots especially in the global south. These time series that we store are sometimes available down to 1952. This goes to near real-time time series, and at the moment we have 6 near real-time networks with about 1,000 stations that are updated in short time periods. And if you look at the slide here on the right side, you can see that there are a lot of observations that just go back down to 15 years. So it is we are very short on soil moisture time series that are longer than 15 years. And of course, for all kinds of analysis, we are very keen to get a very long time series. Just a bit of statistics, the data usage that we have, you see on the left side, downloads by the users going up every year. And also we have between 60 and 80 publications really using the ISMN data, not just mentioning, really working with the data that is downloaded from our service. And on the top right, you see the distribution of our users, again, the US, India, Europe, China, and Australia. We get the data from in all kinds of formats, and then we do the data harmonization. So we are reducing it to hourly data, marking missing values, and so on, do unit conversion, and then get to a unified data format. One part of the data harmonization is also that we do quality control of the data that is provided by our data providers. So we just adding additional information with a flagging system to every data point in our database, and we try to detect implausible and dubious measurements, and we are never deleting data. So this is just an additional information, and we are doing this by using 13 different plausibility checks from 3 different categories. You can see that on the right side on the table. We have the category geophysical range, geophysical consistency, and dynamics of the time series. So these are spectrum-based approaches, and all this is done with the Python module called FlagIt that is developed by the TU Vienna, and this can be downloaded from GitHub. So what are these 3 different categories? One example for the geophysical dynamic range is that we have thresholds for all the variables. For example, we are flagging the data if the water content exceeds the porosity of the soil. The second category is geophysical consistency. So we take another variable, for this example, we take soil temperature, and we are flagging the soil moisture data as dubious when the soil temperature goes below 0, because then oftentimes, or the measurement principle of the soil moisture probes does not is not valid anymore. And then we have some spectrum-based approaches using the first and second order derivative of the time series, and there we detect spikes and plateaus, for example. And yeah, we are trying to improve our approach to data flagging. We try to use AI technology and AI models. And for this, I make a small test for these spectrum-based approaches here in red. So for the spikes, for the negative and positive jumps, I did a little study. So my study was lined out. So I did a manual pre-cleaning of the data. Then I inserted the data with random artificial anomalies, so I know exactly the position of these anomalies. And then I tried out 3 different methods to detect these anomalies then later on. So first flag it, then SAQC, so System for Automatic Quality Control from the UFZ in Germany. And then I tried out a very simple deep learning approach with long short-term memory models. The data preparation, it's like the talk before a little bit. I did visual manual pre-cleaning of 100 time series, and I did it on my own. So of course, it would be better to do it with a second set of eyes, let's say. And I pre-cleaned everything, 100 time series. These time series were up to 14 years long of hourly data. So overall, the study consists of 680 years of pre-cleaned hourly data. And then I inserted anomalies around 3.3% of spikes and drops. Of course, these artificial anomalies are inserted in a random matter. So here you can see such a time series, soil moisture time series. You can see these spikes and drops, and in the orange dots are marking these added artificial anomalies, and in red you see these sudden spikes and drops, and in green you see the normal time series with a spike after a precipitation event and then a gradual decline of the time series after that, a drying period, and then the next precipitation event. So I used a long short-term memory model. I don't want to go too much into detail about that. A very simple one. This is a type of recurrent neural network. This can deal with sequential data, so with time series data. And the LSTM is can keep track of long-term dependencies in such a time series. The take-home message here is that this is really a very simple LSTM model that I used to try to achieve this task of quality control. I will evaluate this then with the confusion matrix and the overall accuracy, so true positives, true negatives, false negatives, and false positives. So let's come to the results of this study. So as a baseline, you see here the evaluation that we have just negative values. So no anomalies are detected. Everything is flagged as good. And then we have, of course, a high number of true negatives, but we have these errors that I implemented as false negatives. So this as a baseline, this gives us an accuracy of 0.968. And then I computed our own routine, our own flagged code that we are using now at the ISMN. And we can see here that we have, of course, some detections of the anomalies, true positives, but we don't get all the anomalies, and we also have some false positives, so correct values that are now detected as anomalies. We are getting a bit better or much better with the SAQC code from the UFZ. So we see here when we have with the Flagged QC, we have false negatives in the tens of thousands. We are here now in the couple of thousands, also with false positives much lower. And we have now overall accuracy of 0.994%. And with our deep learning approach, with the very simple LSTM model, we can catch much more of these anomalies here. You can also see now marked that we have let's say the important values that I wanted to show you. And you can see that we are with the SAQC method, we are, let's say, 1 magnitude lower or better with the detection than the Flagged routine we are at the moment using. But the deep learning approach is in the order of 2 magnitudes better with this simple tasks. So overall, these are, of course, very promising results. But of course, this is just one type of error. We also try to do this with other types of error, with some detection of plateaus and other errors. And of course, this is the error implementation. These are artificial errors. And this is, of course, a little bit different if we have real world data. And I think we have to do pre-training with this artificial data and then do a lot of training also with real world data. The problem is that the real world data, of course, has data gaps, and this is also something that you have to think of if you want to use such a deep learning approach. Yeah, and with that, I'd like to just have to say we also presented this on a poster and the last EGU General Assembly. And with that, I thank you for the attention and hope I can answer some questions. Thank you.
Hello, everyone. Yeah, thanks for having me along today. So I've got a bit of a presentation about our Robin initiative. So it'll be a little bit of introduction about what that data set is and what the network is. But then I've focused on how we dealt with the quality control side of things for this sort of large scale data set. So hopefully that will be useful and interesting. It might be a few overlaps with some of the previous presentations we've heard, but I guess in a way that's a good thing that we're all sort of roughly on the same lines. But first of all, just this opening slide on what the Robin network is or what it's trying to do. So we're interested in a reference hydrometric network. So these are networks of gauging stations which measure stream flow in catchments which do not have many human influences. So natural or near natural catchments. And we're interested in those because if we take away the human influence on our stream flows, we could perhaps attribute any trends in those data more confidently to climate change. So many of you are probably already aware that reference hydrometric networks, they're not a new thing. Many countries already have them, and they're already established networks. So we've seen the one mentioned in France already. But with Robin, we're really trying to bring each country's reference hydrometric network together in one network, and also encourage countries that don't have them already to think about perhaps if they've got any gauging stations in their network, whether they could be designated as a sort of a reference gauge. And we're doing all this because we'd really like to be able to better inform our future IPCC assessments to give more confident claims on how climate change is affecting our stream flows across the globe, and really including floods and droughts as often the extremes which affect people the most. So what is a reference hydrometric network? I've already sort of said it's a network of gauging stations which filters out any human influences or as much as possible. And here's an example of we call it the benchmark network in the UK. There's around about 120 stations, which we've designated as being near natural. You'll notice that there's not so many in central and southern England, around the big cities in the Midlands and London. And there's a bigger proportion of the bigger catchments, especially in more northern areas or more rural areas, as you'd expect. But this isn't new. We first defined this in 2003. I had a bit of an update about 6 years ago. And this is just one example of a reference hydrometric network. There's plenty out there in many other countries. And what are we looking for in a catchment? Here's an example from a gauging station in the north of England on the River Tees. It's a headwater catchment, so it's a small catchment, as you might expect, but the area that gauging station measures is sensibly natural. There's not any major human disturbances. There's not any big dams or reservoirs, and there's no one taking out large abstractions of water, or there's no large modifications to the channel. And then for the stations to be in our network to give us a picture of what's happening, we would ideally like the good quality data, ideally across the high and all the way down to the low flows. And because we're interested in trends, then longish records, perhaps 40 years would be ideal, but really anything more than sort of 20 years would be great as well. And I'm fully aware all of these things are easier said than done. The practicalities of measuring stream flows, I'm sure we're all well aware. There's many challenges. When we look at just how our rivers are impacted by humans, the graphic on the left-hand side shows the proportion where reservoirs affect in the hydrological basins. So, I mean, the darker the red color is almost more areas being affected by reservoirs. And again, here's an example from Great Britain in Wales. We've got a gauging station here just below this massive dam. So obviously that station is not in our benchmark network, but it's a practicality, a limitation. We need to make as humans, we do need to make modifications for rivers, but for the Robin network, we're interested in those catchments where there are little modifications. And I mentioned we're interested in trends and how these human impacts can affect trends. So another example from the UK on the River Thames in West London at Kingston. This is one of our longest gauging stations. I think it is the longest continuous gauging station we have in the UK, with river flows beginning measuring in 1883. And if we have a look at the gauge data and draw a nice linear trend line through it, the red line, you'd be quite right to say that, well, the minimum flows are getting less as we go through time. But this is just the gauge catchment. Of course, the Thames near London, there's a lot of human influences. There's very large reservoirs in the west of London where water's being abstracted all the time. And we're lucky in this case because we can generate a naturalized series. So taking out those, the abstractions, we know how much is being abstracted by the water company, so we can sort of add that back in to the river flow record. And if we have a look at the plot on the naturalized data, the trends actually reversed. So this is why we're really aiming to look at these natural catchments. And I'll say natural and near natural. I mean, having very pristine catchments would be amazing, practically potentially impossible unless you're situated in, I don't know, the north of Canada or New Zealand or something, especially in the UK where I'm from. We're definitely relying on that near natural phrase. We're a small island with a lot of people, so of course there is some human influences, but we're just trying to pick the ones where there are the least. Yeah, and as we all know, measuring high flows is difficult. We have things like weirs going modular, so they're not performing in the way they're meant to. In higher flows, we have floodplain flow, which may not be represented by our gauging stations. And you can see in this example, the flows are truncated after a certain threshold. And similarly with low flows, they're not easy either. In this example of the gauging station, we've got a huge slab of concrete, a weir across the river, trying to measure this trickle of water coming along. Things like weir cleaning and algae growth on the weir can affect our low flows. But back to Robin, this is where we are at the moment. We've got about 30 countries involved, and also about 60 people, because it's not just all about the data. We've built a network of data, but also a network of people who are interested in this. And the people in the network have been vital to designate whether the gauging stations are natural or not. And it's that local knowledge that we're really relying on. As I always say, I might know a little bit about river flows in this little bit on the map, but it's certainly not. Certainly, I couldn't say we are really relying on the local knowledge to assist us. So the 30 countries, all the black dots on this map are the sites in the Robin network. It's about 3,000, and that's where we are so far. And this is our sort of first version of the data set. And we've deposited this data, or the data that we're able to share, in an openly available data center, which will be available in November, the end of November this year. We've also we've got a paper in review at the moment, a data paper that will come out alongside or just after the data set, depending on how well we get on with the reviews. But yeah, so we're in this open data set. Unfortunately, we're not able to publish all 3,000 stations. That's due to data sharing issues, or we're just not able to share other people's data in certain countries. But we are able to share around 2,400, or just a bit less than that, station. So that's the daily flow data alongside metadata for each of those stations. And yeah, as I said, that will be available later next month. So that will be something to have a look for. Thinking about data quality, we had a set of criteria for the Robin network where those criteria that I first mentioned in the beginning, where we were looking for good quality data, near natural, and records of more than 40 years. If they were satisfied, we gave them the level 1 data, and that was perhaps you could use that for analysis of the extremes. And then perhaps where there was data where it didn't have that record length that we were hoping for, we gave it the level 2 data, or perhaps the data quality wasn't deemed as good. We gave it the level 2, so we could still include as much data as possible within the data set. And so the map at the top is the level 1 sites, and then the map below is the level 2 sites. But all the data are available, and that's sort of a guide of what we think, but it's open to be used however people think it should be used. So how do we do the quality control? We started off with a visual inspection. So we've heard about that already with Laurence. presentation. Perhaps some of these things are highlighted here are quite similar. We've got a team of 3 hydrologists from the UK National River Flow Archive visually inspected the data. We perhaps looked through about 2 years at a time and just flicked through them. We looked on linear and logarithmic scales, and we were really looking for things like in the plot, so things that are a bit odd, strange dropouts where the flows just drop straight down to 0. Again, linear infills for quite a long time, or perhaps this is after some winter ice instead. In this top one, there's a bit of a change during the record. Perhaps we mused perhaps that it was using perhaps monthly max data in the early record, and then at this point changed to daily data. Perhaps is one explanation. And also because, again, we're interested in those natural catchments, we were looking for things where it suggested there was something a bit not natural going on. So I don't know, it is very subjective, but in this example, sort of quite regular influx of flows perhaps is not as natural as we thought. So we were looking for those kind of things as well. And what we did is that the 3 National River Flow Archive hydrologists looked through their section of sites and then made comments and looking for anomalies. And then once we'd all been through them all, we got together in a group and then reviewed each of the comments where we thought there was something not quite right, and then decided what to do with it. So if stations showed signs of not having a sufficiently near natural regime, we removed them from the submission. So we removed about 77 or so sites. But where there was some examples like this one at the top, we just edited the data series. So we removed this first section and kept the second half of the data. Or in this dropout, we would just removed a section of the data and just had it as missing data instead. And we made about 300 or so edits to the data that had been submitted. And when I say edits, I mean just removing a period of data. We weren't changing flow values or anything like that. So that was our kind of main visual inspection of the data. And I guess as Lauren said, the data that was submitted to us will have been checked by the measuring agencies and the data providers. So it really is just another level to try and weed out any additional anomalies in the data. As well as this sort of visual inspection of going through each site year by year, we looked at some higher level quality control that might perhaps steer us to issues with any of the stations. So we did this eco analysis where we looked at a simple equation, looking at the potential evapotranspiration and the precipitation and the flow. And in this, we highlighted that some catchments had a negative evaporative index, which suggests something's not quite right with the data. So thinking about why that might be, there's some actual and potential reasons following some investigations we did. A lot of these biggest ones were differences in units, so something really practical that we asked for all the data to be submitted to us in meters cubed per second, but that wasn't the case for every site or every provider, and that was missed up until now. So it was a good check to like pick out these biggest anomalies, which is probably mostly down to units. Because we're doing this runoff calculation, there may have been errors in or anomalies in the catchment area that was being provided or derived by us. which could see these sort of negative, this negative index. And also we were using a global rainfall project, which perhaps it might perform really well, but there might be some cases in some areas it might not perform as well. So there were some reasons we thought. So we were able to look at these lister stations and investigate them and fix them, particularly where there was errors in units, or we could check the catchment area was sensible, things like that. So that was done, and the data updated where necessary. We also tried to just compare it to some other global data sets. So we chose GSIM as a sort of benchmark global data set to see that roughly if the stream flow signatures looked similar. And in a lot of cases they did. I mean, some of the colors in sort of Europe are similar, in Brazil, similar. There were cases where there were differences, and I think we probably put that down to the fact that the GSIM is including all different types of data, engaging stations, where in Robin we're only focused on the near natural sites. So it's a bit of a practical difference between the two data sets, a different objective for them. And lastly, another piece of bit of quality control again to see whether there was any major sort of issues jumping out that was a problem with the Robin dataset. We had a look at the annual mean river flow trends and compared them to GRUN. And again, it was a case of just seeing that roughly are the trends similar. And again, if we have a look at some examples in Europe, in most of mainland Europe, there's some declining trends, and they're reflected quite similar with the red colors. In the north of the UK and Ireland, the blue colors are positive trends and yet reflected as well. So it was kind of, these approaches were more high level approaches, just sort of to give confidence in the data set that we had, and to make sure that there's not any obvious errors. And combined with the visual checking and then the anomalies that were found through some of these high-level checks, we feel that we've done a good job of doing some quality control on this large data set. Yeah, and that was the approaches we took for quality control. But just as a summary, going back to Robin as a whole, how you could get involved if you would like to join the network, or perhaps you're sitting there in a country that wasn't colored in on our map. We didn't include your flag, but you do have some data that might be designated as near natural that you'd like to be able to provide to the network. Then be really grateful if you could get in touch. Perhaps you just have some contacts in some other countries that might be able to pass on to us, and we could approach them. That would be great as well. Because although we've nearly at the end of next month, we will have a published data set. After that, once that's published, we're going to sort of relaunch the Robin network, and we'll be striving for a data set version 2, with the hope that we might have some more data, some more countries involved, some more people involved. And it might just be new countries, but also updating the current data, maybe adding on a few years of data as well. If you're not a data provider, once the data is freely available, you could help analyze the data. We've had a quick look at trends in our sort of first initial analysis, but once it's out there, we'd really encourage people to use it and run with it. It's not just useful for climate detection. You might be able to use it for model evaluation or hydroecology, just some examples we thought about. And we've also provided some code libraries for running like trend analyses and stuff. So they're available on a GitHub, and I can share the link for that as well. So yeah, it'd be great if you can, if you're able to engage, that'd be great with the data set. And we're happy to hear any thoughts or challenges with the data, or any plans you might have with it. We're happy to hear, and if we can help. But yeah, really the main thing is to spread the word about Robin, so we can continue adding to and improving the data set, and we'd be really appreciative of that. And lastly, just the last couple of slides. It is a bit of a reality check. There's a lot of issues with stream flows, as we know. We tried our best to do good quality control on the data with the resources we have. But again, how much do we really know about the records? Artificial influences is a limitation in a global context. There's going to be places in the world where all the rivers have artificial influences due to perhaps water supply or something, and that is a limitation. And then land use and land cover change, it's not something we've explicitly being able to look at, especially land cover change over time. Again, we've been relying on the local experts to give us a set of stations which they think of are near natural, and there's not been any major changes over time, but we've not done anything sort of quantitative about that. And lastly, a really practical one, working with different countries is fun. Perhaps with the logistical challenges, we've had people on the west coast of America and people in New Zealand. We're more than happy to try and, if we're running a workshop, we'll definitely record it. We might try and run one early UK time and late UK time to try and involve as many people as possible. And if we can accommodate anything for perhaps where you are in the world, then that would be something we strive to do. And yes, the quest for reliable hydrological data never ends. This is one of our benchmark networks in the UK again, in the Cotswolds in southern England. It's a really nice natural station. It's a good gauging station, good quality data from this weir. In 2022, sorry, we had a big drought in the area in the UK, and the black trace on this line is flows going below our 1976 drought, which is like the standout drought in the UK. Everyone talks about it every time it gets dry, and they go, is it as bad as 1976? And it was at this gauging station. But since then, the data providers have raised suspicions about the low flows post 2017. So perhaps we've got the significant downward trend in the Q95 flows. So perhaps it's a constant thing to keep on top of. We can't just add the data to the data set. There needs to be a sort of review, a regular review, to make sure that we're keeping on top of the data and we're not allowing any anomalies to creep in, perhaps. But yes, I think that's all for me. Here's all the people at UKCH that work on Robin, and there's also, of course, more importantly, the 60 people from the 30 countries who are listed here on this slide, which I'll just leave it for a second. But that's all from me.